Okay. Thank you, Isabella. Welcome to the second seminar on energy, who is handled by our institute, by CNM IMB. And this one is more focused on power electronics for more efficient and sustainable energy. And this is also lined up with the creation of the International Energy Efficiency Day, which we are celebrating here as well. And we are going to present 3 of the most outstanding projects in power electronics, one focus on energy generation, and all of them are expected to contribute to a more sustainable and energy efficient world. The last one, but not least, is given by Xavier Muñoz, and it's about fuel cells that transform bacterial activities into energy. So I'm going to hand the presentation to my colleague Xavier Perpiñà, who is going to present the European project SAFEPOWER, safe and more renewable wide bandgap and ultra wide bandgap power converters for medium voltage converters, transforming power distribution into DC medium voltage grids. So thank you, Xavier, for the opportunity of sharing your research, and the floor is yours.
Thank you very much for this very nice presentation. I'm going to share the presentation properly. It will be that one. And can you see my screen?
Yes.
Yeah?
Please.
Okay, then let's start. Well, I should say that this project has recently started last October, so results they are not going to be shown here, just the aim of the project and the framework of this project. So if we go to the summary or outline, I'm going to talk about the introduction and talking some topics about the evolution of power systems in energy delivery, the main challenges and solutions in the energy sector, why MVDC conversion is it could be the solution to all these things. And after, I'm going to highlight a little bit how it was the Horizon Europe call that we were awarded. After, I'm going to present the SAFEPOWER Consortium, the challenges that we want to face, and finally, if I have time, I'm going to talk about the conventional techniques that will be performed and explored in this project. Let's start with the evolution of the power systems in the energy delivery chain. And here, this is the traditional power system that you have a source that after is distributed among several points between the residential consumers, commercial, industrial, business consumers, and after industries, okay? But this has changed because we have increased the complexity of these systems, because we have several points for doing this renewable conversion, that it can be done at home, but also it's planned to set up several places to cover in interurban strategies for supplying this electrical energy. How or why it's taken this solution in this way? Because there are several challenges. The first one is that we want to replace the energy source and use renewable solutions. Right now, we are at least or more or less over the 30% in 2023, and we expect for 2050 reach the 62% of global energy produced by renewables. This requires the use of batteries, and these batteries should be connected efficiently to the grid. But after we want to reduce the transmission losses, that is very related with the efficiency of these systems, and we want to overcome the power outages. That it means that there is a cut in the supply of energy. After electromobility challenges, I mean, because they are consuming this power. And finally, when we go to the cybersecurity threats or threat of terrorist attacks, it's interesting to have these power sources distributed among a given area. So everything shows that the good solution is do the decentralization of energy and have a self-sufficiency energy, and try to provide more intelligence to the power converters for managing these things. And after, we need a kind of high-level intelligence that will be controlling all these connections. And this is how we reach the MVDC conversion. The MVDC conversion means that through a medium voltage direct current distribution line, you can be able to connect all these things to supply or to extract the energy for doing that these systems will be operating. Here you can see some details of the different conversion stages that are thought. And in this conversion, it's required a kind of smart control. Okay. So what we are looking for with this kind of strategy, increasing the efficiency, make the renewable energy integration easier, look for compact and lightweight systems, improve the power quality, look for a good electrification of transport, and finally create DC microgrids. That this goes in the idea of the energy decentralization, and provide energy to the industrial applications. Some examples in this sense are data centers, industrial plants, or future smart grids. And I'm going in that direction because the main challenges are related with the conversion efficiency and the semiconductor technology limitations that they show with the current silicon technologies. Controlling the thermal management and reliability of the power components is critical, mainly within the power converter, and this is very, very important. But there is a lack that is very important, that the MVDC equipment and converters are not still available in the market. And if there are, they are very complex, and they need to be improved in this sense of reliability. And finally, the future trends is to adopt this technology in grids using the last technology advances in wide bandgap devices, and after explore also the ultra wide bandgap devices and check if they can be applied for this kind of conversion. This leads to the proposal or opening a call in the Horizon Europe that is focused in photovoltaic generation and wind generation of energy, that is to explore this kind of converters that will be connected in an MVDC environment with these main requirements. The first one is that these power converters should have an enough performance, durability, and the cost effectiveness that will be related with the next generation of power systems. To do this, there are two main challenges. The first one is developing this kind of components. That is the first challenge, that they should be efficient, reliable, and the package should be optimized, and with the main target that this is to reduce the cost of this technology and product. And after, adopt in a second challenge the condition and health monitoring of these components, okay, where it's seeked for the junction temperature estimation for doing a kind of control in the converter, and also determine the degradation and lifetime of the components and the self and the same converter. As a result of this call, 3 projects have been awarded. The first one is SAFEPOWER. This is the target of this presentation, but there are 2 other ones. SAFEPOWER is focused on using artificial intelligence and data-based condition and health monitoring for assessing, in this case, kind of final application scenario, that is the solar conversion. But in flagship, the approach is different, is performed at package level, and 2 kind of demonstrations will be performed. It will be in the solar and wind conversion, and the coordinator is CIRCE, that is a technological center here in Spain. And finally, Mobilife is more focused on the grid level perspective of these approaches, where the whole distribution line is demonstrated, where the main energy generation step is the wind. Okay, if we focus on SAFEPOWER, this is the consortium. There are 10 partners, where you have 2 enterprises, 5 universities, 3 research centers, and involve 5 countries. Let's show what is the first challenge. The first challenge is to provide the key enabling technologies. We target to construct 3.3 kV SIC power devices, but also we want to do a kind of prospective with devices with higher breakdown voltage. If you increase the breakdown voltage, you are decreasing the complexity of the final converter. If we focus on the SIC power devices, what we want to do is to follow eco manufacturing, reducing the cost of these manufacturing steps, and we target to do 2 kind of devices. One with using a planar technology and integrating several sensors, and another one that will be very performant using trench technology and integrating the free-wheel diode inside of the device. To have a kind of comparison, this is that in one case we will have a more rugged device, and on the other hand we will have a more performant device. This is the same to compare, for instance, a car that is oriented for rally racing or a Formula 1 car. Okay, the travel or the way that they should follow will be dictated by the circuit that you are going to use, and you can establish a kind of parallelism between converters, the complexity that you are going to find in the operation within the converter. In any case, we want to also reduce cost, designing smaller devices and optimizing the on resistance of those devices. Here, what we are going to do is also to optimize the strain inductances for finally obtaining the following benefits. First of all, we will obtain a more efficient converter, more affordable because the devices will be less expensive, more compact because we can increase the switching frequencies for these devices, and finally we will obtain less distortion, and the final converter will be less complex. As in a similar way, we are going to do a kind of prospective analysis, constructing lateral devices based on gallium oxide. More details on that will be provided by Amador later on. And the thing is that we will obtain similar benefits on the final converter thanks to the increase on the breakdown voltage that offer this kind of material. Okay? And the next challenge is to improve the resilience, the reliability, and the maintenance cost for these MVDC converters. For doing so, what we are going to use are disruptive techniques for electrothermal power device analysis. In the first step, we are going to identify thermal sensitive electrical parameters for doing the junction temperature monitoring. But in parallel, we are going to develop new techniques to be applied in these technologies. The first one is using the AA RLD for wide bandgap and ultra wide bandgap devices. After use the electroluminescence for MOSFET SiC, and use the scattering parameters for degradation analysis. With this information, we are going to construct artificial intelligent models that can be used for the control of these devices and improve the reliability at converter level. And finally, with all this information, with these key enabling technologies, we are going to propose new topologies enabled with the devices that we are going to develop in the framework of this project. And this is, sorry for the 3 minutes, but this is my presentation. Thank you very much.
Thank you very much, Xavier. I think we can leave the questions, the round of question of answers for the end, and we can move to the next presentation. The next presentation is today. All the speakers are named Xavier, but me. The next speaker is Xavier Jordà. He's gonna present his research related to smart switching cells and transforming mobility with modular solution for all electric vehicles in the framework of SCAPE project, which is funded by the European Union. I think we can move directly to the presentation. So Xavier, the floor is yours.
Thank you very much, Amador. Now I think it's okay. You can see my slides. Yes. Okay. Thank you very much, Amador, for the kind presentation. I will try to present the main activities focusing on CNM, IMB-CNM activities in this European project, switching cell array-based power electronics conversion for future electric vehicles. Sorry, no. Well, who is SCAPE? SCAPE is a Cluster 5 Horizon Europe project with a consortium of 9 partners based in several countries across Europe, with expertise on electronic mobility, research in power devices, converters and packaging, modeling, control systems, as well environmental life cycle assessment. The project is coordinated by IREC. And why we have moved this project on? The motivation came from the fact that 20% of the total greenhouse gas emissions in Europe came from the road transport, including every kind of terrestrial electric vehicle, ranging from cars to heavy-duty trucks, including also light-duty trucks and motorcycles. And these emissions can be drastically reduced if this mobility, this transport, is electrified with energy coming from renewable energy sources. The objectives of the project are to standardize all kinds of electric vehicles, power, electronic converter design methodologies, to reduce the engineering and manufacturing cost of these electronics, to increase the powertrain, the electronics and the motors performance, and to perform health management tasks also on these electronics, and to increase the electric vehicle acceptance and contribute to the European transport industry. What we propose in SCAPE to undertake these objectives? Well, first we propose a modular and a scalable system architecture using multi-level converters. Multi-level converters is a kind of topology of power converter with many benefits from the performance point of view. And these kind of multi-level converters include a big number of power semiconductor devices in switch mode operation. We also propose to integrate the two main converters, the power circuits which are involved in an electric vehicle, which are the traction inverter and the battery charger. And we also propose to use for the implementation of these circuits, we propose to use the chip embedding technology. I will go more in detail further on this technology, then I will provide more details. Also, the project proposed the use of digital twins and advanced controls, use of eco-design approaches, and experimental, of course, an experimental demonstration at the end of the project. As you can see here, the main element of the sorry, I'm looking for the pointer here. The main element of this approach is what we call the switching cell. The switching cell is a small modular and smart circuit, which is included several times in the higher level parts of the circuit, what we call the converter legs. And these converter legs are again combined in a modular way to develop the full converters. But in any case, the main element of these power electronic circuits are the switching cells, which include one or more electronic devices, like, for example, silicon carbide MOSFETs. As you can see here, this approach, these are the converter legs of the multi-level approach. This approach allows using the one kind of switching cell and combining these switching cells in a smart way. This approach provides the possibility of implementing the power electronic circuit required for any kind of electric vehicle, ranging from the two wheels to the heavy trucks. And also the current levels can be also in any case, in all of these cases, the current level and the power required for the vehicles can be also increased by combining in parallel these switching cells. What do we do at IMB-CNM in the project? Well, in the project, we will investigate, design, and develop the switching cells and their integration using the mentioned chip embedding approach. Chip embedding consists in including the power devices inside the printed circuit board stacks, as shows this cross-section schematic here, instead of using the devices in a discrete package or in a power module externally to the printed circuit board itself. We will see that this approach, of course, increases the compactness of the solutions and has other benefits. You can see here a cross section of a real embedded PCB with here silicon carbide MOSFETs from Xavier Electronics, which is the PCB manufacturer we have been collaborating with. Secondly, we will investigate also in the project the technologies required for enabling the chip embedding integration. Placing semiconductor devices inside the PCB requires very specific interconnection techniques, and these techniques had to be set up. And finally, we will also investigate and characterize the SiC MOSFET's robustness and electrical performances used for implementing the prototypes. Okay, and here you can see the main persons involved in the project. Well, related to the switching cells design and development, this work has been and is being performed mainly by Mariana Raya in her PhD work. And as you can see, the schematic of the switching cell, which includes in this case 2 silicon carbide MOSFETs and a shunt resistor, plus control electronics, is implemented in this quite a small PCB, allowing a very high level of integration, as I mentioned before, but also allowing the possibility of developing smart modules, because we have inside the PCB the power stage, but very close we have also the control stage with the SMD, the surface mount devices, which are on top. You can see here a picture of one of the first prototypes, which are in the final application are liquid cooled. You can see here a cross section of the PCBs developed at CNM. We can see here the main switch, the main silicon carbide MOSFET switch operating this switching cell, a protection, additional protection silicon carbide MOSFET, which is called the iFuse, and the shunt resistor, okay? The electrical characterizations of these prototypes show very, very good behavior. Concerning the static characteristics, the switching cell, as you can see here, provides a very low on-state resistance, around 30 milliohms, and bidirectional current carrying capability. And we also obtain very high switching frequency operation, even higher than 50 kilohertz, as you can see in these waveforms, where we are switching 400 volts and 30 amps in the switching cell. This high frequency operation capability comes mainly, apart from the use of wide bandgap semiconductors, from the fact that the parasitic inductance of the switching cell can be minimized using this chip embedding approach. Inside the PCBs, we have the current, the main current path, where we can cancel magnetic fields, providing a very low in parasitic inductance in the board. You can see here at high frequencies, we are reaching parasitic inductances well below the 3 nanohenries, which is a very low value. In fact, we have evaluated this parasitic inductance reduction around 80% when compared with standard solutions. On the other hand, this implementation has been also very robust. We have demonstrated that we can withstand short circuit events, which are abnormal events that can occur during the operation of the vehicles. And as you can see here, the switching cell was conducting up to 1000 amps under 400 volts for 2.5 microseconds and is not destroyed. In addition, we included also additional protection circuits which can switch off the switching cell in case of abnormal operation, as you can see here. Okay. Then another critical aspect of this kind of switching cells is their thermal behavior, the capability for dissipating the heat generated under operation. In this case, again, we have obtained very low values of thermal resistance, approximately 45% below standard values from commercial and conventional solutions. This you can see here the thermal impedance curves, experimental and simulated, of the switching cell developed here, and these values have been obtained by a very accurate and optimized design of the internal structure of the switching cell using thermal bias, etc., based on finite element simulation and multiphysics simulation. All this is possible only if we can put the power devices, in chip format, in bird eye format, inside the PCB. This requires, as I mentioned before, very specific interconnection techniques on the top side and on the bottom side of the dies. And the dies, the chips, are connected, in fact, on a copper lead frame, a copper piece, okay? The chips need relatively thick copper layers on top, on the gate and on the emitter pads. And the chip require on the bottom side their interconnection to this copper lead frame using silver sintering materials. The analysis and the investigation on these two aspects constitutes, in fact, the PhD work of Emma Solà. As you can see, Emma has set up a shadow masking copper evaporation process in the clean room, where we have been able to obtain these thick layers on top of the dies. We have a very good control of the thicknesses we can provide, and you can see here that this top side copper layer is required to obtain the interconnection of the silicon carbide MOSFETs with the tracks of the PCB, okay, in the chip embedding implementation. On the other hand, for contacting the backside of the chips, we need to use a very performant die attach layer, which is based on silver sintering die attach processes. We optimize the processing of these materials first from an analysis of the material, of the parture material, which is based on silver micron nanoparticles, and also on the optimization of the process, which consists basically on temperature, pressure, and time processes applied to the dies and to the silver sintering material. A big effort has also been performed for screening and selecting the best materials. There are many possibilities at commercial level now, but we have selected the silver sintering materials that show the highest stability, because we are in fact in an automotive environment which is quite strict concerning reliability and robustness. Then we selected the materials which show the best stability during aging test. You can see here the acoustic images of the die attach of one device after 1,000 hours aging at more than 250 degrees C. And as you can see here, some materials show quick degradation, but others show very good stability, okay? And finally, another aspect which is very, very relevant is to control the thickness of this die attach during the process. When the silver die attach layer is processed, there is a contraction. For example, in this case, we start from around 40 microns thickness on the initial material, but at the end, we obtain 30 microns thickness of the die attach material, and this is very critical for chip embedding. Then also a big effort has been provided here to control these processes. And what's next in SCAPE now? Then, well, now we are developing all these switching cells, and at the end of the project, we plan to develop a demonstrator, a 100 kilowatt demonstrator, which in fact could be compatible with a traction inverter of a medium car. Okay, thank you very much. That's all from my side.
Thank you, Xavier. Thank you for your excellent presentation. I think is a very important topic. This one of packaging and correct heat management of chips. So the next speaker is myself. In fact, we have seen first presentation was about systems and big energy systems. Second presentation was about packaging, was about modules, but also about packaging. And my presentation will be about devices and materials. This is a kind of all the value chain of power electronics. And I'm going to share the screen. Let me see. Xavier, do you see my screen?
Yes.
Sorry,
Yes.
Isabella. Okay. Thank you. It is okay. So do you see full screen?
No, it's not full screen.
Okay, it is now full screen?
Now it is.
Okay, perfect. So I'm gonna present, let me see if I close that. Okay, I'm gonna present new activities we are carrying out in the power electronics groups here in the ICN2. Sorry, I've been many years in the ICN2, sorry, in the CNM, regarding gallium oxide power electronics. And I'm going to present the background because projects had just started, the background about our previous research on gallium oxide. This is in fact a collaborative project between many institutions. Several of them are leading research around the world. I must thank you in particular Ekaterina Chikoide, which is in Paris, and Mike Jennings, which is in Swansea, and also some other collaborations as Edgar Putanovs in Latvia, and David Rogers, Jacob Leach, and Huarong in Taiwan, Cherniak, Florida, and Jürgen in Paris. And also people from the power device groups in the ICN and in the Microelectronics Center, and in particular to Pepin and Miquel. And these activities are now being funded by several projects, in particular some French, which are in reality pan-European, Gallia and GoPower, the Spanish national that here started, the GAFO Power, and the European project, which was presented in the first presentation, which is SAFEPOWER. As Xavier mentioned, one line is about fabricating gallium oxide devices. So let me just make a brief introduction because probably all of you know, but maybe not all. I mean, a wide bandgap semiconductor is some semiconductor which bandgap is larger than the one of silicon, which is not difficult in fact. But in practice and for power electronics is something that is around 3 electron volts, which fits well with silicon carbide and gallium nitride, which are the basic and the most researched wide bandgap semiconductors. And a new field has just, in the last decade, has just emerged, which is related to ultra wide bandgap semiconductors. And basically, there is an informal definition of what is a ultra wide bandgap semiconductor, which is the semiconductors which bandgap is larger than the one of gallium nitride, which is 3.4. So we are speaking about a group of materials which is typically some nitrates like aluminum nitrate or boron nitrate, and some oxides like gallium oxide, aluminum gallium oxide, or other combination. And why these materials are important for electronics and for power electronics in particular. For optoelectronics, they are solar blind, so they are properly transparent, as I will mention further on. For power electronics, what happens is that these materials usually presents a critical electric field which is larger than silicon, much larger. And having a larger critical field means that with the same chip area and thickness, you can get much lower on resistance. So you can make all the systems smaller, which is very important, for example, for electric vehicles. To make an example, but in any case, in any power application, that is an important thing. And this is given, I mean, the way one semiconductor is better than other for power electronics is given by one thing that is called the Ballica figure of merit, which is here depicted, which depends on the mobility, which is typically the electron mobility, and the critical electric field. And as you may see, that depends as a factor of 3 on critical electric field. If we go to this map, we immediately see that the strong point of gallium oxide is that the critical electric field is much larger, not only than the one of silicon, which is here below, is 20 times larger, but is several times larger than the one of silicon carbide. So that means that the expected performance of the devices will be much better. That is the basic idea. And that is what the wide bandgap semiconductors do. They extend the operation of power electronics to larger voltages and larger frequencies, which is typically the area of interest of silicon carbide and gallium nitride. And with gallium nitride, which is probably the best situated ultra wide bandgap semiconductor, what we plan to do, or what is the expected niche of application of gallium oxide, is to extend much further these power ratings to systems that are currently very difficult to electrify, like marine transport, grids, and further on. So, speaking about the material is presented in several polymorphs, which only one is stable, which is the beta phase, which is monoclinic. And it has a band gap of around 4.8, which means that is completely transparent to the visible spectrum. And it has been a kind of unexpected material to make research on, because as you may see in that graph, it was a kind of average material until the first demonstration of crystal growth was done in Japan, and then it was attracted a lot of interest now. The first gallium oxide device was just launched in 2012, so some 10 years ago, also in Japan. And from then, it has been an impressive advancement of the technology, to the point that now the best demonstration of gallium oxide are beyond the potential or the maximum performance of silicon carbide or gallium nitride, especially for very high power ratings. So basically, which has been our contribution to the field since we started something like 10 years ago on working on gallium oxide. We have published, if that means something to any of you, we have published some 20 papers or more on the material. And I think that the most important contribution from our sides maybe is the evidence that the gallium oxide can be a p-type material, so can have an acceptor nature, but that was against the theoretical approaches and results at the time. Another experimental observation we made is that the critical electric field may be underestimated because it is considered a value of 8 millivolts centimeter, but it can be larger than this value. That means that the device can work even better than we expect. Another milestone that has to do with material development it was the first demonstration of a ferroelectric grown on top of gallium oxide, and it was applied to a certain kind of solar cell, which is called ferroelectric photovoltaic, so full photovoltaic effect, and we get some record performance as well. And regarding material as well, we demonstrated that at that time, the combination of gallium oxide with zinc oxide, which is the spinel zinc galate, was the bipolar semiconductor with the largest bandgap. Here are what we mentioned before, what I mentioned before, which was that the theoretical predictions is that there is no option for whole conduction in gallium oxide because the valence band is flat. We demonstrated that this is not the case, and gallium oxide can have perfectly free holes in the material. So that opens the door to make any kind of device like in silicon or silicon carbide, so MOSFETs or IGBTs. That it's regarding the critical electric field. What we observe is that the critical electric field of gallium oxide can be as large as 13.2 megavolts centimeter, which is significantly larger than what was expected to be in the simple model, because there is no other reason than that simple model to assure that it is 8 megavolts per centimeter. And one of the properties, one of the features which is important for optoelectronics of gallium oxide is that it's completely transparent. That means that all the solar spectrum pass through the material without any absorption. That is not the case for traditional transparent conduction oxide like zinc oxide or indium oxide or the like. And we use that concept to grow a ferroelectric and to illuminate them. And we observed that this material was a perfect platform for demonstrating the Bull photovoltaic effect, which is related with the polarization state of the ferroelectric and traditional TCOs quench that effect. And regarding the last one, it was demonstrated that the combination of gallium oxide and zinc oxide can be bipolar, can present holes and electrons. And at that time, as I mentioned before, it was the largest, the material with the largest band gap where this was observed. And what is missing? What is missing? Well, what is missing in Europe in particular are devices. And what we're planning to do in the project, we plan to do devices, no? And we are currently making diodes and making lateral transistors. So as a summary, we might say that power electronics is central to the management of power electronics. Sorry, is central to the management of electronic energy, which is central to mitigate the climatic crisis of this century. That we have now discovered a new family of materials which are very promising for providing devices with more enhanced performance compared with not only with silicon but also with second generation wide bandgap materials like silicon carbide or gallium nitride, and that we are I think we are ideally suited here in the CNM to make devices because it's timely and we have the funding for doing that. I think it's all. So I'm gonna stop sharing. Let me see if I can do it. Sorry. Okay. So I'm gonna now, sorry, I need to keep speaking. I'm going to present last speaker, last but not least, Xavier Muñoz. Let me see. Xavier Muñoz is going to present some very interesting work about transforming bacterial activity into energy in a kind of devices that he calls fuel cells. And it is very peculiar way, no? Because it's another way to achieve greater energy sustainability with the development of energy sources based on microorganisms such as bacteria and power electronic devices in the agricultural sector in the localized, continuous, and autonomous manner. So I think it's an excellent talk. Thank you, Xavier, for preparing that. So the floor is yours. You can start whenever you want.
Well, thank you, Amador. Yeah, well, I will present the two projects, the Sol2Power and the CONFETI project, that are related to this topic, this microbial fuel cells topic. First of all, I will explain a little about the motivation that is related to energy production, of course, but also to the emissions of CO2 that we have right now. I will introduce Bio, that is the company that we are collaborating with in the framework of these two projects. And then I will introduce the soil microbial fuel cells concept and how we are implementing in the two projects that I'm working in. First of all, well, that's clear that the energy demand is growing. And there is a problem on that because there is the commitment of the Commission and Europe to reduce the CO2 emissions. In fact, they want to reach zero emissions in 2040. And if we check what's happening right now, even if the total emissions are growing, if we make some calculations, for example, if we determine the amount of CO2 emitted per kilowatt that we are producing, you can see that from 2000 it is more or less stable, and it is even reducing due to the pushing on these renewable and clean energies, especially solar and wind. And it's precisely in this point where Bio, the company that I'm collaborating with, have found a room for improvement. Bio is very clever in this sense because this is what they say. They are powering things by nature. They realize that maybe we don't need a lot of energy or to produce big amounts of energy in all the cases, but there are some electronic devices that they don't require a lot of energy. For example, an LED that is in a smart city or a panel or these kind of things. And in this sense, they produce and they sell right now a battery of products They have the biopanels, the bioswitch, biolumina. Most of them based on the concept of a microbial fuel cell. Here you have, for example, the scheme that you can find in the web page of this biopanel and everything that they say. Two things that I think that are very important of this biopanel is that even if it resembles the structure of a conventional microbial fuel cell with the anode and cathode, I will explain it later, it has two things that make it very interesting. The first one is that they claim that it has zero or negative CO2 footprint. And it is because they incorporate some plants on top of it that they can absorb CO2. Look at this point where they say that every year they can absorb an amount of CO2, which is reducing a lot this footprint. The second thing is that all of this structure is based on biodegradable and biocompatible materials. And this biodegradability nowadays is very important since it is against microplastics and the accumulation of these plastics. Here you have some examples of places. These are these biopanels already installed in some roofs and subsoils for producing energy, just for example, these LEDs. The energy that they can produce is not very high, as you can see here. It's just 15 watts-hour with panels that are 7 per 7 meters. But let's see what is a microbial fuel cell. And for this, I would like to start explaining the difference between a battery and a fuel cell. In a battery, well, both of them are based on chemical reactions, quite similar in some cases. But the difference is that in the battery, this closed structure, the reaction is taking place spontaneously, and it is storing and delivering the energy when you need. In the fuel cell, everything is slightly different. Even if you have an anode and a cathode for the oxidation and reduction reactions, in the case of the fuel cell, we have a fuel, an energy source. In this case, it's hydrogen because it is a nitrogen fuel cell, and we have the two chambers separated. We have a membrane that is semi-permeable. It allows the flow of protons, and we have another element that is very important, is also the catalyst. The catalyst, we have a catalyst here that is helping on this reaction that is not taking place spontaneously. How different is this when you compare with a microbial fuel cell? Okay, we have exactly the same structure. We have the anode, we have the cathode, we have the redox reactions, and we have the membrane that allows the protons to cross. But the main difference here is precisely on the fuel and on the catalyst. In a microbial fuel cell, the fuel is the organic matter that in the case of soil is in the soil, and the catalyst is bacteria. Bacteria is taking this organic matter, and here you can see an image in your right. I think that you can see my pointer. All of these are proteins that finally what they are doing is to produce an electron flow. This electron flow is generating a proton flow, and then the bacteria can survive, is producing energy. But we can distort that. We can take these electrons that bacteria is producing during its metabolism to produce energy by itself. How? If we connect or we put an anode close to this bacteria, the bacteria can transfer these electrons in three ways. Some bacteria that have these proteins very close to the external membranes can directly transfer electrons to the anode, and then the energy production is direct. In some cases, they have like wires to do this, biological components that can transfer electrons directly to the anode. But in most of the cases, you need a soluble redox mediator to transfer the electron to this anode. Here, you can see the final reactions that we will have here. And as you can see, one is this. This is the metabolism one. This is what's happening in the cathode. That is just the reduction of the oxygen. The final products that we have are water and CO2 that, as I said, in the case of bio, they can collect thanks to these plants that transform this CO2 directly on biomass. what's happening with these microbial fuel cells that Bio is developing? They have soil, they have plants. In this case, in the plant, the difference between a plant and a soil microbial fuel cell is that in the plant, we are using everything that the plant is releasing in terms of organic matter to as metabolite for the microbial fuel cell. Then here we are closing everything. We are closing the cycle. And they are producing this kind of microbial fuel cells, and you can see that the power is not very high. And this is one of the problems. But the second one, and maybe the most critical one, is that they need a lot of time to produce some power. Here in this case, it was close to 5-6 days, but in general, they need more than 14 days. And the reason for that is that you don't incorporate directly the microorganisms on the transducer, but they are just colonizing it over time, producing what is called a biofilm. And here in the biofilm, we have bacteria that can transfer electrons and others that they cannot. And it means that we have partially covered with microorganisms that are not producing energy. And this is not interesting for us. That's why that since I have been working with in the study of the interaction between cells and transducer for many years, Bio contacted me. In fact, my research is mainly focused on using these micro and nanotechnologies to study how cells can transfer information, in many cases also electrons, to transducers. And thanks to the micro nanotechnologies, I can produce elements that are in the size of the cell, and then they are very sensitive or more sensitive than the macro scale ones. What I proposed to them was to modify this anode and create a bioanode using silfibroin that, as you know, I have been optimizing in the clean room for many years. Now we have a silk technology at wafer level where we can deposit silfibroin in a very controlled way. Depositing layers between 40 nanometers and 10 micrometers with very high precision. The difference in these layers is less than 5% in the whole wafer. And we also optimized the processing of these silk fibroin layers with EBL, as you can see here, with the advantage that the final developer is water, which means that we can dope these layers with biomolecules, for example, enzymes or bacteria or even cells, and then do the processing without affecting the activity or biological activity or even structure, as I will demonstrate later. This is what we did at the very beginning. We wanted to see what was the limit of our technology, and we saw that we could perform patterns of around 100 nanometers. Below that, it was difficult because sometimes the pattern was not perfect. Then we decided that it was our technological limit, and it is with membranes that already contain enzymes. And what we did was to check the activity of these enzymes after the processing. And what we saw was that the processing itself, the EBL processing, was not affecting the activity of the enzyme. Then we had a protocol to immobilize biomolecules without affecting them. And another very nice thing was that once immobilized inside the membrane, they were stable even to the action of solvents. As you can see here in this green image, this is the percentage of activity that was in the membrane compared to other membranes like an amorphous silk, that it was not crystalline, or nitrocellulose. And we were improving this stability a lot. Once we optimized that, what we did was just to modify the carbon fiber electrodes that Bio was developing, and we incorporated in them electrogenic bacteria selected from the soil and also redox mediators in a way that we can induce the transference from the microorganism to the transducer, even if it is not electrogenic. I can show you here some images of some these carbon felts with the silfibroin membrane. And also here, this is an image to demonstrate that these bacteria that were immobilized following this protocol were still alive. They are green, they are alive. With this protocol, if they dead, they will be something like this, more red. And with this, we improved the performance of these microbial fuel cells. From the very beginning, the voltage was much higher, also providing energy in less time. It was from 4 days or 3 days, the time necessary to produce energy. Now we reduce this time even to 0 days. From the very beginning, they can produce energy, and we were almost doubling the current that it was supplying and also the power. Where we are applying this? We are working in 2 projects with 2 different applications, all of them to the agri-food. Why agri-food? Because agri-food is very demanding in terms of water. 70% of fresh water is consumed in agri-food industry, and also in energy. 30% of the global energy is consumed in this sector. That's why we decide to go for an improvement in this sector involving both water and energy supply. Energy supply is obvious. With this microbial fuel cell, we can provide energy, for example, for sensors, but in this case, we wanted to improve also the second part, this water demand. Coupling this microbial fuel cell to sensors and to a bistatic water irrigation valve that was automatically open and close when it was necessary. Now we are in the in-field assays, demonstrating in-field that it is performing well. In CONFETI, we had another objective. We realized that probably these numbers are not fully correct because it is from 2014, but I don't have them updated. But in agriculture, most of the energy is on the production of the fertilizer. Here it's 29%, in some other places it's 15, 17, 20, but it doesn't matter. That's very important that the production, transport, storage, and delivery of the fertilizer is a very important part on the energy demand related to agriculture. Then we decided to go one step further and to produce directly the fertilizer in the field and deliver it in situ. Well, how we wanted to do that? We produced some membranes that can capture CO2 and nitrogen from the environment, and with the energy that the microbial fuel cell is providing, they can produce urea directly in the field. And then with the irrigation, we can deliver directly without any storage on other type of expenses. This is the objective of CONFETI. We are in the initial stages of development. We already have tests that we can produce urea in very small quantities, and now we are just coupling all of these structures. And once I presented the 2 projects, I think that I can finish my presentation. And thank you for your attention.
Excellent, Xavier. Excellent. I think now it's time for questions.
Hello, this is Luis.
Hello, we can see. We
Just,
can hear you very well.
yeah, just a question for Xavier Muñoz. You said that you have improved the time to energy of the biofuel cells. But my question is on the other side, how do these fuel cells age with time? Because this is something you want to keep there for as long as you need, but how do they age?
Yeah, thanks, Luis, for the question. These microbial fuel cells, since they are based on organism that is alive, they suffer from changes in the environment. It means that we have implemented microbial fuel cells in the United States in different regions, and we saw that during winter, the energy that they can provide is much lower because the amount of live bacteria that they have is less. But there is another part that is very important as well, that is that since they are microorganisms, it is a self-healing system, which means that once we are in summer again, or autumn, the microorganism is again alive, active, and is producing energy again. Our estimation of lifetime of these systems is 10 years. But the ones that we have implemented in the United States have been operating for 2.5 years up to now. Then we don't know exactly if we will reach this 10 years time.
Okay, thank you.
Thanks.
Hi, I have a question. I'm Neus. Do you hear me?
Yes.
Okay, I have a question for Xavier Jordà. But it's something related to the overall project, the SCAPE project, which I found very interesting. And I saw that within the project, they also plan to make environmental assessment. Can you explain a little bit what are the indicators you're going to look at? Because I found that very interesting.
This, thank you, Neus. This task in the project is performed by IREC. They have some researchers and a department which are specialized on that. And basically what we will do with them, because we are collaborating with them, is to analyze the impact of the new solutions proposed in the project compared with more conventional solutions. For example, let me mention in our case, in the tasks we are performing here at the IMB-CNM, we will use silver sintering as die attach material, and in other more conventional solutions, solder alloys with heavy metals are used. Even sometimes lead is used for this soldering die attach layer. This is something that will be, this is more related to the eco-friendly, let's say, design. And concerning the life cycle assessment more properly, for example, the chip embedding approach is replacing many packaging materials, such, for example, ceramics, by PCB, by printed circuit boards. And the printed circuit board industry has well-established procedures and mechanisms for recycling these printed circuit boards. Then this is an example of what we will evaluate. The benefits from replacing some critical materials, such as ceramics in the packaging, for other materials which are more suited for recycling, etc.
Thanks. I also have another question for Xavi, if nobody else wants to ask. Xavi, in the biofuel cells, you talk a lot about bacteria which are in the anode. What are these fuel cells using in the cathode? How do they convert oxygen, or how do they reduce oxygen?
Yeah, thank you, Neus. I was not explaining that because it was not part of my job, and I didn't want to, because there is a pattern on these things. What I can tell you, Neus, is that the materials that we use in the other electrode are also biocompatible and biodegradable, and not based in critical raw materials, and they are not organic. Although I have to say that we want to try also with other bacterial formulations. But it's Eurecat working on this.
Okay. So the pattern is theirs.
Yes.
All right. No, thanks. I was curious because you didn't mention, and I was like, oh,
Yeah.
what's in there? What's in there? Thank you.
Xavi, this bio company is a Spanish one?
Yes. It's located here close to Barcelona. It's in Viladecans.
I have a question for Xavier Jordà and the chip embedding. So just for the philosophy of the approach, so with embedding, you get a more compact system, but also I guess it's a system that is more difficult to fix. I don't know if people are fixing PCBs today or not, no? But so there should be a trade-off, no? The final system should be really robust so that it will last, or it should be very cheap so that it's very easily replaced. I don't know in which part of this field of play falls the chip embedding for power.
This is I mean, the eternal trade-off between miniaturization and integration and repairability, for example. It's easier to repair a faulty transistor in your old, I don't know, TV board, or on your old radio board than repairing one transistor in the monolically integrated die that now makes the world. Here is the same. But in any case, this trade-off that you mentioned is what justifies all the efforts on obtaining robust and reliable systems. This is why we have big efforts on analyzing the robustness, the reliability, to understand the behavior of the devices which are placed inside. This is why we integrate protections. As you have seen, one of the benefits of chip embedding is that you can put close to the power stage, which is perhaps the most sensitive one. You can place control circuitry. Then there are several stages of protection circuits. I have shown only a few of them, but there are all over temperature protections also included in the switching cells. The shunt resistor is used for sensing the current. Then you can at every moment you can detect if there is an overcurrent, etc. Then yes, there is a trade-off. It's not possible to repair a faulty device inside the switching cell, but the switching cell it's more robust than their traditional counterparts.
Xavi, which is the TRL that you have now with
which Xavi? Sorry, which Xavi?
You.
Okay.
Xavier Jordà.
Okay.
Sorry, Xavi Perpiñà, but I miss yours, so I cannot ask you. Which is the TRL that you have now for these switching cells, embedded switching cells? So you showed results, very nice results. Are you confident that you have got it?
What do you mean exactly?
How close to real implementation is the development?
Well, yeah. Next spring, I will respond very precisely to you, because we are now developing the second generation of switching cells that have been again designed here at IMB, and they are now the Xavier, which is the PCB company we are collaborating with, is developing the new generation of these switching cells, which in fact are very similar, but we modify some aspects. And Deep Concept, which is a French company, we are also collaborating a lot with them, is developing the main board where all these switching cells will be connected. This is also heavy. I mean, it's tough to develop this board, but the plan is to obtain at the end a converter leg, a system which is modular. You can combine several of them, etc. And the idea is to test this in a test bench at 100 kilowatt, which mimics the behavior of a car. In fact, among the partners is Tecne, which is a is an Italian manufacturer of specific vehicles. And there is also AVL, AVL Turkey and German. AVL is one of the main players on automotive electronics. And the idea is to, I cannot know to provide you a TRL number, but it will be very high.
Okay, thank you, Xavi.
Any other question, please?
I have a last question. I know you're all hungry, but let me make an end question for Xavier Perpiñà. I'm curious about how these three sister projects ended up in the portfolio. So you submitted many projects in different consortia, and the reviewers selected three that were complementary, or how this ended up? And another question is, do you have to interact at some point?
No. The thing is that there were several proposals, and at the end they selected these three projects, okay? And we've got I don't know if there will be any kind of strategy, as you have said. We have no knowledge on that, but we have started to share information about our ideas and how to tackle the let's say the aims of the Horizon Europe proposed, okay? And after sharing our approaches, we have realized that this is how we want to do this to face the call, okay?
Interesting. Thank you.
Any other question? So I think we are virtual, but I think we may thanks again the speakers, because I think it has been a very excellent session. And I think with that, I think we can close the session. And thank you all of you for being here. And well, we expect to do this kind of sessions in the future, presenting what are the results, the outcomes of the project in a few years. So thank you very much, and take care.
Thank you, Amador.
Thank you, Amador.
Thank you.
Thank you.